Now, speaking of books, the book we're using is the big white book, which I see there, by Corman, Lysis, and Revest, otherwise known as CLR. And they do, in the first few chapters, a very nice review of the basic mathematics that you need for this class. And they talk about solving recurrence relations the same way I'm going to talk about it. In fact, I usually, even when we don't use this book, I usually Xerox those few pages for students and hand them out. And so I recommend that you look at that. I think it's in the 4th chapter. In fact, I think I wrote it down. Where they talk about recurrence relations is somewhere between page 58 and 70. So there's a section in there where they're talking about recurrence relations, and it's worth taking a look. And they talk about recurrence relations the way we need them in this class, and not the way that you'll find them in a typical discrete math textbook. And so the basic thing, let me just invent one here. Plus 3n. So here is a particular recurrence relation. I'm interested in T, which is well, it could be TA, P. It could be looking at the number of primitive operations that algorithm A does when solving problem P. But I'm going to suppress all the subscripts here. And we'd like to know what this function is, and what we're able to do in looking at the particular algorithm is we're able to say, well, I don't know what T of n is exactly. I don't have a closed form solution for it yet. But I do know that it's twice T of n over 2. Okay, so whatever T of n over 2 is, it's 2 of those, plus 3n plus 6. Okay? Or typically, we know it's less than or equal to that, but in doing the analysis, we're going to be getting an upper bound. You just look at that, that recurrence relation. And then you need a base condition, or initial condition. What happens when the value of n gets small? All right, and what we want out of this, so this is a typical recurrence relation. And what we want out of it is a closed form solution. So we want a function of T of n which does not refer to T on the right side. Okay? So how do we solve that? What's the general technique for solving such, how do you approach such problems? Anybody know?
Draw some kind of a tree first, Expand it out a little bit to see how it behaves first.
Right. Okay, any other suggestions?
You can try the master's theorem.
Yeah. Okay, that's another thing. Now, you didn't have this course here, did you?
Yeah.
Oh, you did? Okay. You did, but not for me.
No.
I don't recognize you, yeah. And there's a third way. There's 3 common ways that I like to solve these things. One is was suggested in the back, which is to draw out a recursion tree. We'll do that in a minute, and that's talked about in the book as well. The second technique is to use the master method, which is in the book as well. And what's the third method? Talk to a mathematician. Yeah, that's a possibility. The third method is you just look at it and you just see the answer. And after a while, that will happen, especially these particular recurrences. So actually, who can tell me what this solves to? It's what?
Substitution.
Okay, yeah, and substitution is actually another idea, which is if you can guess the right answer, you can substitute it, and then typically prove that you were right by induction. That was another possibility. But the guessing part of that well, it depends on how good your guess is, whether that's going to be an efficient approach. But I'm just saying, eventually, you'll just look at this and you'll know what the solution is. And what is it?
Log n. And log n.
Yeah, this is certainly. I hope. Yeah. No. When I look at this, I say, oh yeah, of course that's theta and log n. All right, but how do we get to that? What almost always works for problems that we're going to encounter is just unwrapping the recurrence a little bit until you see what's going on. So this is the unwrapping method. They call it the book the tree method. And you have to do the unwrapping a little carefully so you don't, so it provokes your intuition properly. If you do it at the wrong level of detail, you won't see the pattern. But the key thing for trying to unwrap something like this is to pick a value of n initially that's going to be informative. So you can already see in here, well, there's a halving phenomenon going on. So that tells you, first of all, what value of n do you want to play with? What kind of n do you? I'm going to take a look at a specific example, a specific value of n. A what?
Even.
Definitely even. Anything else?
Power of 2.
A power of 2. Because there's the successive halving that's going on. And in order to get the picture cleanly, you're going to want to have a value of n which is a power of 2. OK, there's an infinite number of powers of 2. Which one are you going to pick?
8.
2, 4, 8. Probably if you pick 2, 4, 8, you're not going to see much of what's going on. On the other hand, if you pick, I don't know, what's the biggest power of 2 that I can name off the top of my head? 1,024 is about it. If you pick one that's that big, it's probably going to be too big to see what's going on. So like n equals 16 is a good choice. All right. So we're trying to see what t of 16 is. And unwrapping this recurrence, it says, I don't know what t of 16 is, but what I do know about t of 16 is that it's equal to twice t of 8. OK? Plus some other stuff, which I'll put up in a moment. So I'd really like to know what t of 8 is. And in fact, I'd like to know it twice. OK? But I also need to know, what's also happening is that you're accumulating here in this recurrence relation 3 times n, so that's 3 times 16, plus another 6. So t of 16 is twice t of 8 plus 3 times 16 plus 6. OK? So here's our running total. Well, I don't know what t of 8 is. OK? But I can do the same thing. I can say, I don't know what t of 8 is. And it's very important to say that. Otherwise, the magic doesn't work. I don't know what t of 8 is, but I do know that it's twice t of 4 plus 3 times what? 8. Yeah, that's probably a point I don't need to emphasize in this class, but it's a point of confusion in the undergraduate world. A lot of people would say that, oh, what you have to put back there is 16 again. OK? This n is changing. OK, the value, it's a variable. So each t8 becomes a t of 4. We need to know what t of 4 is. OK? But each t8 also left to the side 3 times n plus 6. So what's left over here is, well, we get 2 of those things, which are 3 times 8, OK, plus 6, right? And actually, as I was saying, you want to do this unwrapping in a way that provokes your intuition. If I had just collapsed this all to a single number, I mean, I can do the arithmetic here. 3 times 8 is somewhere around 24, plus 6 is 30, and 2 times 30 is 60. So I could have just collapsed this down to 60. But it wouldn't be terribly, it wouldn't help my intuition if I just collapse it to a specific number. And actually, to get my intuition a little bit better, this 8 here, it's useful to describe that as 16 over 2. OK? Well, all right. So I know that t of 16 is going to be 3 times 16 plus 6, and that's going to be twice 3 times 16 over 2 plus 6. All right. And then I don't know what t of 4 is. If I only knew what t of 4 was, then I could just, plus these 4 times t of 4s. You know. If I knew what those were, then I'd be in good shape, but I don't know what those are. So, but I do know I can unwrap this again. Maybe it was too big. I should have started at n equals 8, but you're seeing the idea. Okay. So what's over here? Four times 3 times 16 over 4 plus 6. Okay, that's fairly good, although to help my intuition a little bit more, what about this 4? It's what? It's 2 squared. So this is actually 2 to the 0 times that. 2 squared, sorry. And, well, I don't know what t of 2 is, but it's getting a little tedious. I know that t of 2 is, again, just applying that recurrence, is, well, it's all these t1s plus what? Two to the third times 3 times 16 over 8 plus 6. And actually these, now I can start seeing the pattern even better. 2 squared 2 to the third. So I've got this running sum. These numbers have to add up. Plus then I got all these t of 1s. Well, now I'm down to the base case where t of 1 I picked as 0. And so those all go away. So I know that t of 16 is equal to this sum. And I've written it in a way that's hopefully intuitive, that helps our intuition. So in this particular example, we could just sort of eyeball this a bit. What seems to be going on in each one of these terms? I mean, you've got something out here and something here which is the same. So those guys cancel, right? 2 to the 2, 2 to the 2, 2 to the third, 2 to the third. But you have this other term, this 6, which has to be multiplied by those power of 2s. Okay? So the thing you want to do at this point is to look at a pattern. Okay? And from this pattern here, write out in some abstract way or in some precise mathematical way a summation which captures what's happening here. Okay? So this is a sum. I equals 0. This is going to be my I here. And the first thing we see is that I is running from 0 to what? Log base 2 of n. Okay? Log base 2 of n. All right? And then we're seeing 2 to the I times 3 times 16. Well, actually, that 16 was our n. Okay? N divided by 2 to the I plus 6. Is that right?
N minus.
Oh, okay. Yes. Log base 2 of 16 is 4, right? And 3 is 1 less than that. So at this moment, let's be precise. Right. Later, we'll see that I'm almost always off by a plus or minus 1, and it almost never matters. But you might as well, if you see it, do it right. Okay, well, we can simplify this then. This is then summation I equals 0 log base 2 to the n log base 2 minus 1. 3n, because those guys canceled, plus 2 to the I times 6, okay? Well, what's going on here? All right, so summation, this is just a constant 3n. So this part just becomes 3n log base 2n minus 1. And then we have a summation 6 times 2 to the I equals 0 through log base 2n minus 1. Okay? So we now have this n log n term, which we advertised was going to come out. And then we also have something here. Okay? So what does this summation look like? Now we have two choices when we look at this summation. We can apply a geometric sum, which presumably we can all remember how to do, or actually we better do that. 2 to the I, sorry. Well, somebody tell me about the summation of powers of 2's. What's the summation I equals 0 through k of 2 to the I?
2 to the k.
2 to k plus 1.
It's 2 to the k plus 1 minus 1, okay? So this is a very fundamental fact here. So in our summation here, this thing is going to be 6 times 2 log base 2n minus 1. And then this thing is just n. So this is 6n minus 1. And so what we got here is 3n log base 2 of n minus 3n plus 6n minus 1. And that's theta of n log n. And why don't I write the base of the logarithm here?
Just a constant term, constant difference.
Right, because the theta notation has already grouped together everything which is any two functions that is just a multiplicative difference, where there's a constant which is a multiplicative difference of the two, are also theta of each other. And when you change the base of a logarithm, you're just changing the multiplicative factor. And so it's never needed in this kind of notation to say what the base is. And being basically lazy, you omit it. So I think I've made something fairly simple here into something fairly complex. Okay? But the unwrapping here to see what is going on is the paradigm that I'm suggesting is the most useful. Now, if we didn't have this 6 out here, let's suppose we didn't have the 6. And tell me something about what's happening.
Same.
This is a simpler case and something that's also very common, which is that we're getting the same sum at each level. So very often in this kind of unwrapping, what happens is you get the same sum at every level. And you see that by doing some unwrapping for a few times, and you realize, oh, there's something happening out here, but the same thing is happening here, and they just cancel. And I'm getting 3 times 16 at each level, 48. And then to get the sum, I just have to concern myself with 48, or actually 3, it's 3 times n times the number of levels, which is about log base 2. And then you'd immediately say and see that this is n log n. That happens. The other thing that happens is that when you do the summation, you sometimes get things that are more difficult to solve. You don't get things that are the same at every level. You don't get some very simple change that's happening at every level. Here the change was this power of 2 times 6. That was what was different at each level. Nonetheless, by using the geometric sum and by using particularly some manipulations of the logs, you're able to simplify that summation. So that's technique number one for solving recurrence relations, particularly divide and conquer type.
Question.
Now, yeah,
But you put 1 into this equation, that's not equal to 0.
if I put 1 into that equation, if my base,
Yeah.
if this was 1,
No,
then
I know. I mean, the T1 should be equal to 0, but you put, if you put n equal to 1, that equation not equal to 0.
Oh, okay. So here's, as I
So
said,
I
I'm
think
almost always off by
okay.
plus or minus 1. And this is a good example of it. Yeah. The number of levels that we actually went down when we had to add in a sum was not log base 2n. The last level, when we got down to n equals 1, we had to put in, we got zeros there. So the levels that actually contributed to the sum was in fact, well, it was just 3 levels. And so that was one of the reasons that we didn't want to put log base 2n. Is that your point? Let me make a more general point. We only have 2 seconds. You've got to look at the final level here to see whether or not that level is going to be in this general sum or not. And if it's different, which it oftentimes is, if this was 17, you just have to explicitly handle that in the summation that you set up. But it almost is never going to matter. As long as this is just a constant, it's going to come out to be theta of the same result anyway. Okay. Look at chapter 4, because the next step in treating recurrence relations is the master method. And it really, all this is doing is encapsulating in a more abstract way what we just did. And it'll give you some rules for going from the form of the recurrence relation to asymptotic relationships, big O, omega, theta. See you next time. Look at the homework. Let me know if there are problems.